Today's lecture is on acid-base balance. It is a lecture on the understanding of acids and bases with the concepts of acidosis and alkalosis. The human body is in acid-base balance when hydrogen ion production is equal to hydrogen ion loss from the body and pH of our body fluids stays within the normal limits. We take in acids and bases in our diets daily and produce them also in the body by metabolism. Let's look at some definitions. An acid is any chemical that releases hydrogen ions in solution, while a base is any chemical that accepts hydrogen ions in solution or produces hydroxide ions. In a solution, if in that solution the hydrogen ions and hydroxide ions are equal in quantity, then the solution is neutral. Therefore, in a solution, an increase in hydrogen ions or a decrease in hydroxide ions makes the solution acidic. So, if my hydrogen ions go up, I become acidic, or if my hydroxide ions go down, I am still acidic. While an increase in hydroxide ions or a decrease in hydrogen ions makes the solution basic. Now, this is neutral. They are equal, hydrogen and hydroxide. Here is an acidic solution. Hydrogen ions going up, basic. Hydroxide ions going up, or acidic. Hydrogen ions could be going up, hydroxide ions going down, still acidic. Or hydroxide ions going up, hydrogen ions coming down, basic. Now, to maintain this constancy of the solutions and body fluids, we use buffer systems in our body. Buffer systems play very important roles. The buffer systems could be physiologic or chemical. A physiologic buffer system involves the urinary or respiratory systems, which will stabilize the pH by excreting hydrogen ions, bicarbonate ions, or carbon dioxide. While a chemical buffer system is a system or substance that binds hydrogen ions or releases hydrogen ions to the solution, depending on the rise or fall of hydrogen ion concentration in the solution or in our bodies. Examples of a chemical buffer would be the bicarbonate, phosphate, and protein systems. Now, the acidity of the substance or the alkalinity of that substance depends on the substance or chemical near it. Meaning, for example, if I have an acid in a solution and another acid which is stronger is added to that solution, my initial acid will behave as a buffer in relationship to the stronger acid. The same goes for bases. If I have a strong base and another base is added to it, if this next base is stronger than my initial base, then my initial base will now behave as a buffer in relationship to the one that is actually stronger. Examples of strong or weak acids and strong or weak bases. So we're looking at, let's say, hydrochloric acid, which is our stomach acid, and lemon juice as strong acids. Examples of strong bases are oven cleaner, lye, sodium hydroxide. While we find weak acids in milk, coffee, bananas, we find weak bases in egg whites, in household bleach. For us to express acidity or alkalinity numerically, we use the pH scale. Now, on the pH scale, 7 is neutral, less than 7 is acidic, while greater than 7 is basic. So, here's what my pH scale looks like. Here's 7 right here. This will be neutral. Now, if I go along this line, following my cursor up, that's 7, that's neutral. Water has a pH of 7, so water is neutral. If I go to the right of 7, this way, I'm becoming more basic. If I go to the left, this way, from 7, I'm becoming more acidic. The body pH is about 7.4 right here. That's the average. And we'll have a range of 7.35 to 7.45. You can see this is a narrow range. A rise or fall in pH of the body, of the human body, could have very, very serious consequences. First of all, we have to remember that a change in pH by 1 point, so let's say I go from 1 to 2, that is actually an increase in concentration by 10 times. So again, if I change my pH by 1 only, I increase concentration by 10 times. So let's say I change my pH from 1 to 3, which is 10 times 10, that's 100 times rise. If I change my pH from, say, 4 to 7, I change it by 10 times 10 times 10. That's 1,000 times increase in concentration. So if my pH goes below 7, here, if it goes below 7, or if my pH goes above 7.7, it's a little bit above normal, this could be very, very fatal. It could kill us in a few hours. If my pH goes below 6.8 right here, or it goes above 8.0 from here above, this could kill us in a matter of minutes. The thing is this, we have to remember that in the human body, if our pH goes up, we are now basic, more alkaline. We call it a state of alkalosis. If my pH goes down here, we are now more acidic, so we call it a state of acidosis. That brings us to the topic of acidosis and alkalosis. A rise or fall in pH, as we said, a rise or fall in pH of our body fluids can be very dangerous. It could have serious consequences. First of all, we want to be sure that we maintain homeostasis within this limit here, right here. Maintain homeostasis. So normal range 7.35 to 7.45 with an average of 7.4. Above 7.4 is alkalosis. Below 7.35, acidosis. Now, in acidosis, what is going to happen? In acidosis, I'm going to have hydrogen ions going into the cell. Here, potassium ions will diffuse out of the cell. If my hydrogen ions diffuse into the cell, they become buffered by proteins here. Remember, I have protein buffers, they'll become buffered by proteins. Therefore, although I have positives going into the cell, I don't actually see them. So it means that my cell becomes more negatively charged. This makes it more difficult for me to depolarize the cell, meaning my cell has decreased activity. Therefore, I'm going to have my central nervous system being depressed, which will result in a coma eventually. The heart becomes weak, doesn't beat that strong. The heart finally stops, fails. The blood vessels would dilate drastically. This will lead to a drastic drop in blood pressure. On the other hand, if I have alkalosis, hydrogen ions now are leaving the cell. Here, leaving the cell. Potassium ions going back into the cell, diffusing back into the cell. In this situation, there's a net positive charge inside the cell, making it easier to depolarize the cell. This leads to increased activity. And the cell membranes will become more active, which will lead to things like muscle spasms. You have muscle spasm, Charlie horse, if you call it that. In the brain, I'll have seizures. Then there will be tetanus. Finally, respiratory muscles will become paralyzed because of too much activity, and they will start walking. To maintain homeostasis, the human body gets to use more systems apart from the buffers we talked about earlier to keep the pH constant. The two systems in the body that we rely on are the urinary system by way of the kidneys, which will excrete hydrogen ions or bicarbonate ions, and the respiratory system, which uses the lungs and will excrete or retain carbon dioxide. Here are the two systems. Our cells constantly produce carbon dioxide and hydrogen ions, which means these two coming in here into my blood can make my pH fall. What do we do? Carbon dioxide is sent to the lungs and is held. Hydrogen ions sent to my kidneys and removed. Here's the equation we're looking at. Carbon dioxide added to water will form carbonic acid. This is under the influence of carbonic anhydrase, CAH, acting here. That's the enzyme. The same enzyme, carbonic anhydrase, will break down carbonic acid to hydrogen ions and bicarbonate ions. So, in acidosis, what do you see? In acidosis, my hydrogen ions will go up, bicarbonate ions will be low. So, acidosis could be metabolic. That means that my kidneys have a problem, they are not functioning properly, or they are retaining hydrogen ions, okay, if it's acidosis. Or it could be respiratory, meaning my lungs have a problem and they are not functioning properly. Now again, if my lungs have a problem, my kidneys tend to compensate for that problem. They tend to try to make it work. If my kidneys have a problem, my lungs will try to compensate, okay, by working harder. So, back to acidosis. We are saying if our lungs are unable to remove carbon dioxide will accumulate in the body. Here, carbon dioxide accumulates in the body, which means we become acidotic. On the other hand, we could be alkalotic.